It's great to see so many people here, and it's great to welcome Kumar Murty to give today's talk. Kumar has his undergraduate degree from Colloquium University in my hometown, PhD from Harvard, where you worked for Dante, and has received many honors, which I won't list because I'll give you time to talk. He's just finished being department chair at the University of Toronto, and it's wonderful to have you here.
So amongst the many honors is the honor of being with you today. I was in Columbus many years ago, so it's good to be back. I thought I'd talk to you about one of the things I'm interested in, have been interested in for the last few years, this concept of the Euler-Kronecker constant. So it's something that was introduced by Ihara, and you'll find, I think, probably the first instance of that term in there's a volume for Grinfeld's 50th birthday, and in that there's a paper by Ihara where he talks about Euler-Kronecker constants. So what are they? Okay, I'm going to define them in a little bit more restrictive setting than what Ihara was actually looking at. I start with a number k. Okay, so that means a finite extension of the rationals. And associated to this thing, there's an analytic object which some of us love very much. It's called the Zeta function, defined by Dedekind, or we call it the Dedekind Zeta function anyway. I'm always nervous about these namings of things. You know, I was about to say it's introduced by Dedekind. I'm not quite sure if it was it or not. But we call it the Dedekind Zeta function. And what it is it's a generalization. So when k is q, this is the Riemann Zeta function, which, as you know, is defined for real part of S bigger than 1 by this infinite series. So I have a complex number S, and it's defined by the sum n equals 1 to infinity, 1 over n to the s in this half plane. And basic theory of the zeta function tells you it has an analytic continuation with a simple call at s equals 1. Now, the Dedekind zeta function is defined similarly in the half plane real part of s bigger than 1. So what you do is you go over ideals inside, you go over integral ideals of the field, and then you take 1 over norm a to the s. So what do these things mean? So what I'm saying is that this is ring here, OK. This is the ring of integers. Okay. So if you like, it's the integral closure of z inside k. And it plays the role of z inside, just as the role that z plays inside q, OK plays inside k. It's a beautiful ring. It's a Dedekind domain, and one can study its ideal theory. And following Dedekind, we know that every integral ideal, every ideal in here can be written uniquely, has a unique factorization into prime ideals. Okay, so A can be written in a unique way. So this is how one recovers the unique factorization that you have in Z. So a long evolution of algebraic number theory, where people realized, firstly, naively, if you take unique factorization as occurs in Z, the naive generalization is false. That is, in a number field, you can have integers which can be factored in 2 different ways in terms of irreducibles. So it took it was a number of decades, perhaps, before people realized the way to fix that is to replace elements with ideals. And then when you do that, you recover unique factorization now into prime ideals. So as a result of that, you can look at these things. And then norm A simply means, if you like, the index of A inside O. And it's a property of this ring that this is always finite. So This is the way one measures the size of A. One of the ways of measuring size of A is the actual number, and you take the reciprocals to the s power. So that's the analog of the Riemann zeta function in the number field. Okay. Now, it's a remarkable fact that there is an analytic continuation. For all this. There's a simple pole at s equals 1. So as you know, the Riemann zeta function, when you try to analytically continue, there's going to be a problem at s equals 1 because the harmonic series diverges. And when you figure out what it's actually doing near s equals 1, it turns out as a function of a complex variable, it's got a simple pole there. And that persists. So there's a kind of a universality here that no matter what number field you take, you're always going to get a simple pole. Okay? The prime number theorem, whether it's over the rationals or over a number field, depends very much on that. The fact that it's always a simple pole. It's not, for example, a naive conjecture might be that it should be a pole of order equal to the degree of the field, something like that. That doesn't happen. It's always a simple pole. Okay, so now you can therefore look near s equals 1. So zeta k of s has a simple pole. So let's say its residue, just write it as c minus 1, s minus 1 inverse. And then let's just look at its Laurent expansion, higher order terms. So some coefficient c minus 1, c0, c1, and so on. Now it turns out, this is interesting, this is a horizontal. How can we go?
We give our students a PhD when they figure it out.
These things are really, really very good in a talk, because one of the problems with math talks is they go too fast. It's very hard to pick up, what's going on, because it takes a while to figure out math. And so that's why I prefer Blackboard to Beamer, I think, because just too much material going by too fast while you're trying to figure out what you're doing. So while the speaker fumbles with the board, you can try to. What are we talking about? Okay, so what happens here is these numbers are extremely interesting. Especially, let's start with c minus 1. Okay, c minus 1, this is the residue at s equals 1 of zeta function, has a lot of what we know and love about number fields all wrapped up into it. So what is it? There's a formula for it. It looks like this. It's 2 to the r1. I didn't tell you what r1 is yet. 2 pi to the r2, class number, regulator, over number of roots of unity, and square root of the discriminator. Beautiful formula. And as I said, it has, this will be not just a lecture, but a course if I wanted to try to define all of these terms. But all of these things are invariants associated to K that in any serious study of the arithmetic of K, you have to get your hands on. Okay? And somehow, these different strands that one has been playing with suddenly come together, very focused, as the residue of this zeta function, all built into one formula. It's kind of a miracle. Okay, so you have this c minus 1 is given by this, and it's certainly not 0. Now, the Euler-Kronecker constant then, by definition, if we denote gammas of k, is c0 over c minus 1. Okay, the constant term divided by the residue. Now, there's another way to write this, which might look a little bit more natural. Namely, if instead of the zeta function, suppose I look at the logarithmic derivative. This is a nice thing to look at, because as you know, logarithmic derivatives of meromorphic functions, their residues are integers, right? So if zeta function has a simple pole at s equals 1, this will have a simple pole at s equals 1, and the residue will be minus 1. All the complexity that was built into that residue is gone. So it starts off as minus 1 over S minus 1. The next term is gamma k. Okay, so another way of saying it, it's the constant term in the Laurent expansion of zeta k prime over zeta k at S equals 1. Okay, so now a couple of things. If I try to first explain why it's called an Euler-Kronecker constant. If k is q, rational numbers, then this gamma k is actually what we call Euler's constant gamma. So it is Euler's constant. So this is by definition the limit tends to infinity 1 over n minus log x. Okay, you know, as partial sums of the harmonic series grow like log x. So if you subtract that, then the constant term is gamma, little gamma. Little gamma is a very mysterious quantity. We don't know, for example, whether it's irrational. Little gamma, by the way, is also another interesting thing, that it skews prime number theory. So I'll say this to the number theorists. You see, the presence of e to the minus gamma in Merton's theorem skews our naive notions of how prime numbers should be distributed. So there it is. It's a number that is there. You can't get rid of it. It's mysterious. We don't even know it's irrational, although we expect it to be transcendental. And it keeps showing up in different places. Okay. Now the other case that you should keep in your mind is the case of an imaginary quadratic field. So suppose K firstly is a quadratic field, 2 join square root of D. Okay, so that's a degree 2. Now in this case, the zeta function actually is divisible by the Riemann zeta function. In other words, you can write this as the Riemann zeta function times another function, which we'll just call maybe Ls or As. Okay, it's a fact that now you can say, well, look, I can take any function here and write it as zeta s times something. It's this thing could be just the quotient. but the point is that what I mean by being divisible is the quotient is entire. This is actually entire. And therefore, when you take the logarithmic derivative at 1, what's going to happen is gamma k there'll be a contribution from this one, which will give you the ordinary gamma, plus this one will just give you the logarithmic derivative at 1. Now the point is that so firstly you have that expression, and the second thing is that we can actually evaluate what this gamma k is going to be. You see, inside this thing, of course, we have the ring of integers. Now, if you take an ideal inside here, or even an ideal class, you can decompose this. You can look at something called a partial zeta function. Namely, you can look at the zeta function associated to that class. What I do is, instead of summing over all integral ideals in K, I only sum over certain integral ideals, so-called those which are the class C. What does class C mean? It means that up to a scalar multiple, they're the same. So somehow you can scale one to the other. Okay? And that's what's used as somehow, this class group is a way of understanding the obstruction to unique factorization of elements. Okay, so you have such a thing. Now the point is, this looks at first like a strange way to decompose this thing, because if you see, I can get the entire zeta function by summing over the c's. Because every ideal, integral ideal, will appear in some class, and so I get this sum, and this is a finite sum. Now there's a beautiful classical formula called the Kronecker limit formula, by which one is able to analyze this partial zeta function. So using that, what one is able to prove is that this zeta function also actually has an analytic continuation. this is again, obviously this will converge absolutely for real part of S bigger than 1. It has an analytic continuation. It also has a simple pole at S equals 1. And the expansion near 1 looks like this, again with a lot of beautiful numbers. 2 pi number of roots of unity times the discriminant. Out of the discriminant. And then some class invariants, which I'll just write like this. So this, some of these terms should be familiar. Pi certainly should be familiar. This is the number of roots of unity in the field, which is finite. This is the discriminant, which I didn't define, but you can sort of guess what it is. And then here's your simple pole. So this thing has residue 2 pi over mu k root 3k. And then you have Euler's gamma. Again, you have log of the discriminant. And then you have this mysterious g of c. Now, this g of c is a so-called class invariant. It's defined in terms of modular forms. It's defined as a special value at a CM point of the Ramanujan delta function. So whatever it is, this thing is algebraic, and you have this formula. And so as a result, when you put together those two formulas, that the zeta function is a sum of all of these over the different c's, you... Sorry? Oh, higher order terms, yes.
Yeah.
I'm sorry. Okay. So this is I wrote the polar term and the constant term and higher order term, right? So therefore, this gives you the formula that gamma k is actually the following: 2 gamma minus log of the discriminant minus 1 over 6 times the class number times log of g of c. Okay, so you get an explicit formula for the Euler-Kronecker constant of a quadratic field. Something I failed to tell you. Something I failed to tell you. For a quadratic field, this factorization is true. This decomposition, all of this is true. However, Kronecker's limit formula only works when d is negative. It's for an imaginary quadratic field. I'm sure some of you were very concerned because I was writing, only for imaginary quadratic fields, you have this thing. People have tried hard to do this for real quadratic fields. You get a mess, total mess, which is hard to recognize. But here it's very beautiful. This g of c is defined by a very simple formula involving the Dedekind, the Ramanujan delta function. Okay, so therefore, you have two examples where you can actually write down a formula, kind of, for the this gamma k. And because those two examples are one studied by Euler and the other studied by Kronecker, Ihara thought it fit to call this the Euler-Kronecker constant. That's where the nomenclature comes from. I might remark here that you could apply a theorem of Baker to this situation and observe that, you see, what are the unknowns here? You have gamma k, which is a kind of unknown, little gamma, which is a little unknown. This is log of an integer. And then you have this rational factor and logs of algebraic numbers, algebraic integers. And so for Baker's theorem, you actually can show that if you got rid of this gamma k minus 2 gamma, the right-hand side is essentially transcendental. Now, I'm cheating a little bit because this thing has some pi, so you have to adjust for the pi's. Once you factor that out, by Baker's theorem, the right-hand side is essentially transcendental. So what you get here, which you couldn't prove for gamma, is that essentially gamma k minus 2 gamma is transcendental. So there's something weird going on here. Now you got a family to play with. This mysterious number gamma, in its isolation, was hard to get a handle on. Now you got a family to play with as you vary the different k's. Okay, good. So now we know what the topic of the discussion is. Okay, next let me explain the connection to L functions. These are ordinal functions. Okay, let's assume for a moment, just for simplicity, that my k over q is Galois. Okay, so that's it. Just for, if it's not Galois, you get a similar formula, a little bit more complicated. Okay, in this case, the zeta function can be factored as a product of L functions. These chi's are going over irreducible representations of the group G. This is some finite group occurring with multiplicity equal to the degree of the character. So chi is the character associated to some representation of G, finite dimensional representation of degree chi of 1. So this is a factorization. These LS chi's, whatever they are, we don't really need to know for now the details. These are certain Artin L functions, which can be defined associated to each representation of G. Okay. Moreover, we know one of the big problems in this area is so-called Artin holomorphic conjecture. And that is that LS chi, if chi is an irreducible character and not the trivial character, then this thing is entire. In other words, has a continuation. Again, as usual, you see these things are defined actually by an Euler product. And you can say that for real part of S bigger than 1, they're absolutely convergent, and so they define a holomorphic function in that half plane. The conjecture is that they can be extended for all S, again, as an entire function. You don't acquire any poles. Okay? Unlike the zeta function, which acquires a pole at S equals 1, these L functions stay entire, no pole. This is, of course, a big problem. It's quite open, and in cases where you know how to prove this, it's either group theoretic trickery combined with class field theory, or a very deep theorem in automorphic forms. But the point is, we don't know this, but we do know this at S equals 1. If you ask me, can L1 chi, can LS chi have a pole at S equals 1? I can tell you the answer is no, as long as chi is not the trivial character. Okay? So we don't know the entirety, but at S equals 1, we do know. And therefore, if you look at you take this formula and then just compute the logarithmic derivative, what you get is a formula that looks like this. Gamma k is gamma, which comes from the trivial character, plus the sum chi of 1, L prime over L, 1 chi. Okay, so chi is going over the irreducible character. So that's a relation, that's the formula for gamma k in terms of logarithmic derivatives of Artin L functions. Okay. Now I make the remark, because it's going to be important, that these LS chi's have a functional equation which relates S, the value at S, to the value at 1 minus S. Okay, there's a symmetry. And therefore, I can also consider what I might call some variation of this gamma k, namely, or variant rather. So I call it gamma k tilde, where I look at the same thing, but now use L prime over L at 0 chi. And there's a simple formula relating the two using the functional equation. Just logarithmically differentiate the functional equation. Okay, why do I want this gamma k tilde? Because this has a conjectural interpretation in terms of periods. I'll try to explain now. So, okay. So you remember, this is another problem that people want to know about. When you come up with a number that occurs naturally, you want to not know just numerically what it is. What is this number? We want an interpretation for the number. And so there is a conjecture that relates this to periods. Let's pause for a moment and marvel at even the thought of doing this. You see, for those who like this kind of language, Artin L functions correspond to motives of rank 0. Periods normally arise in geometry, as dimension 1 and higher. So why would there be any relationship whatsoever between an Artin L function and a period of some geometric object? Not likely at first blush. You shouldn't think there is any such thing, yet there is. So let's see how this goes. So I'm going to define the geometric model. So we start in the case that K is a CM field. So not any field, but a CM field. What's a CM field? It means it's totally complex. In other words, every embedding of K into Q bar goes actually, every embedding of K into C actually goes into C, and not into the real numbers. And it has a maximal subfield, which is totally real. So K plus, totally real. And the index is 2. You just keep the following examples in your mind. Examples, K is an imaginary quadratic field, Q root minus 1 if you like. So K plus is Q. Or you think of K as field of mth roots of unity. And then K plus is Q adjoint zeta m plus zeta m inverse. Okay. So those are good examples to keep in mind. So I take a CM field and look at its real subfield. Now, when I'm in this setting, so what do I have? I have a real CM field. So look at the different ways I can put K into C. There's a bunch of embeddings. Now, whenever I have one embedding, let me call one distinguished embedding, which I'm going to call complex conjugation. The point is, if I have one embedding, I can always compose it with complex conjugation on C to get another embedding. So the embeddings really pair up into, you can pair each embedding with its complex conjugate. A CM type P is a set of embeddings K into C such that phi union phi rho is the whole thing. And phi is disjoint from phi rho. So that means for every embedding, for the set of embeddings, you take one from each complex conjugate pair. That's called a CM type. Okay, now it turns out whenever I have that situation, a CM field and a CM type, I can create an isogeny class of abelian varieties. Let's explain it. If I take this K and tensor it with R, okay, these are over Q, then this can be identified in different ways as C to the n, where the degree of K to Q is 2n. Remember, the degree of a CM field over Q must always be even because it's got this subfield of index 2. So let's say it's 2n. Then tensoring with R, I can identify it with an n-dimensional C vector space, a 2n-dimensional real vector space, therefore an n-dimensional C vector space. And this isomorphism is given by the choice of the CM type. I mean, I can choose which isomorphism I want. I'm saying it's the one where I send x to the vector phi x, where phi is in phi. Okay, so that defines for me a thing. Now I can define an abelian variety. The abelian variety is one of the most beautiful of algebraic varieties. It really is the kind you just fall in love with right away. So what is it? It's a torus. As a complex manifold, it's a torus. Okay, so it's a torus. So it's a C to the n modulo some lattice. So it looks like C to the n modulo lattice. Now, not every such torus is algebraizable. That is, not every such torus can be given the structure of an algebraic variety. If n equals 1, it can. C modulo lattice is always an elliptic curve. That's Riemann or Weierstrass or something in my history. Using the P function, you can embed this into projective space, and you get the differential equation satisfied by the P function gives you the algebraic equation. Okay? Riemann's uniformization theorem tells you any Riemann surface is an algebraic curve. Amazing, beautiful theorem. A Riemann surface is defined purely analytically in terms of complex structure, and yet it has this algebraic structure. It is a curve. Okay, but the higher dimensional version of that is false. You can have tori that have no algebraic structure. So there's a condition on the lattice L for this to be algebraic. It's by Lefschetz criterion. And it turned out in this case, you see, if I take the C to the N as K tensor R, and let's say, for example, I take for L the ring of integers. L ring of integers is certainly sitting inside there. Well, there is the condition that Lefschetz imposes to make this algebraic is automatically satisfied here. Basically, in technical terms, what you need is something called a polarization. And the polarization is just the one who is given by the trace form, trace xy bar. Okay, so there is a polarization, a Riemann form, by which the condition of Lefschetz is satisfied, and you get an abelian variety. So in this CM setting, you're beautiful. Everything is good. You can create the abelian variety. Okay, so this is an abelian variety. Now, what kind of abelian variety? Well, it's a very beautiful abelian variety, because not just any old abelian variety. It's something which is called a CM abelian variety. And CM stands for complex multiplication. I once gave a series of lectures in Chennai on complex multiplication. I announced it as complex multiplication. And a physicist or a computer scientist came to me and said, "Oh, I'm looking forward to your lectures because you're going to teach us how to multiply complicated numbers." No, I'm not. I'm not. It's called complex multiplication because this field K, which is a totally complex field, acts here. You see, not K itself, but OK will certainly act on the lattice, right? And therefore, OK acts on the lattice, and therefore, by tensoring with Q, K will act on the C to the N. So this abelian variety, whatever it is, has the property that its endomorphism algebra contains the CM field that we started out with. Okay. Now let's say we're in sort of the minimal case of this, where by that I mean suppose A is actually simple. That is, somehow it doesn't split up into smaller abelian varieties. That condition can be expressed purely group theoretically in terms of phi. If you do that, so in this case, I will say that in this case, the endomorphism algebra is just K. Moreover, the H1, just singular H1, is a rank 1 vector space, the dimension 1 vector space over K, so one-dimensional K vector space. And the holomorphic, if I look on the cohomology, the holomorphic 1 forms on A. This is, as a vector space, it's C to the N, which is in fact given by, it's given by the C sigma, if you like, sigma in phi. So in other words, for each element in the CM type, there is a holomorphic 1 form, omega sigma, unique up to multiplication by K. So what I do is, here I have one-dimensional vector space, so choose some non-zero element here, C in here, which is not 0. And then for each sigma in phi, look at this holomorphic 1 form and consider the period. Okay. This is well-defined modulo q bar star. Why modulo q bar star? Because I made a choice of the cycle. And any other cycle is a K translate. So when I throw if I replace it with a K translate, it's just going to change this by a multiple of K. So this therefore gives me a period for each element sigma in the CM type. Okay, this then gives us something called the period symbol. is. So therefore, what do I have for K? I have for each choice of sigma and the CM type, I have a period. And this is defined modulo Q bar star. Okay, now what Shimura does is he extends this map to define for any two embedding sigma and tau, he's able to define something which is kind of like a virtual period. Okay, now this comes from a motivic construction. Here I had a very specific, I had a single element here and a CM type here. Now you need to do a lot of playing around with abelian varieties until you find you can split off a single embeddings. So that for each pair sigma tau, you can actually define something which is a period. Now this thing is actually not a period of a single abelian variety. It's a quotient of product, it's a product of quotients of periods of actual abelian variety. So motivically or Tanakian, in some Tanakian sense, it is a period. I don't like these words. So therefore you do this funny business and you come up with what Shimura calls a period symbol. Okay, now you're probably wondering where is all this going. Now there's a conjecture of Kolmez and Yoshida. And what it says is that it says the following. If I take this period symbol and evaluate it at some distinguished embedding, which I'll call 1, somehow think of fields, my fields are already sitting inside Q bar, okay? So that's the distinguished embedding, let's call it 1. Then this PK11 satisfies the following property. Are you ready? Raise this to the degree of the field, multiplied by a power of pi. And this thing is twiddle, which means up to Q bar star, exponential of gamma k tilde minus. Decorations don't tell us that. So the gamma k tilde, remember, is like gamma k, except I replaced, instead of L prime over L at 1, I had L prime over L at 0. Right? The minus means, you see, when I have this kind of CM field, the gamma k here is actually the gamma k down here plus stuff. And that stuff is what I call gamma k minus. Okay? So it turns out that exponential of that is exactly this period. And that's why now this conjecture sort of makes precise a long-held belief by many people in number theory and algebraic geometry that gamma is not a period, but it is log of a period. This is the precise conjecture. Now, this wasn't just pulled out of the air. Firstly, it is mysterious. It should strike you as very, very mysterious. Why? Because this, as I told you, is made up out of Artin L functions, motives of weight 0. This is made out of abelian varieties, motives of weight 1. Okay? There's no reason why the two should be held together like this. But that's the conjecture. Okay, so now where does this conjecture come from? I'll just tell you that it's a generalization, a grand generalization of something called the Chaulas-Elbert formula. So what does this say? It says, suppose I go back to my imaginary quadratic field.
Sorry, Kumar, I lost track of some of the assumptions or conditions you're making. But you need to be restricted on the basis of being able to ace involved, right? So this construction of Shimura, is that reliant on first having PK sigma with a CM p-type that gives you this construction?
That's right. So first you define it that way with a simple CM type, and then you extend it by multiplicativity to any CM type. Okay. So you get out of the simplicity condition.
Okay.
And then to go to a whole CM type to a single element, you need to do a lot of playing, virtual playing.
So in the conjecture, this is
disappears. Yeah, all of that hypothesis disappears. And because now, at the end of the day, you have a complex number, pk sigma tau. I give you a CM field, and you have a complex number. And for any two embedding sigma tau, you have a complex number. And this is saying somehow pk11 picks up exponential of the gamma constant. And this tilde, I repeat, is up to q bar stop. Okay. What does Chawla-Selberg say? Chawla-Selberg says this is true in the case of an imaginary quadratic field. And the way it works here is like this, that the conjecture, you see the gamma k minus, this conjecture can be written like this: pk11 squared is exponential L prime over L0 of the character corresponding to this field. That's what that conjecture says. In the case of an imaginary quadratic field, that's what the conjecture says. But the point is, we know how to evaluate the logarithmic derivative of Dirichlet functions, not just quadratic characters, but Dirichlet functions. And this can be written in terms of gamma functions. So this is up to q power product gamma A over D to the following nice exponent, mu k chi k of A over 2 times the class number. So it's a product of gamma function values at rational points. This is a theorem. Okay, and this is classic, is kind of classical. And then it's Chawla-Selberg that says, in this case, you're dealing with an elliptic curve with complex multiplication by k, and this is a formula for the theorem. Okay, so therefore, the theorem is true. The conjecture is known to be true in the case of an imaginary quadratic field. Notice that as you correctly, as you're saying, the conjecture can forget about the abelian varieties. I mean, it's saying for every CM field and two embeddings, I have a complex number. If you don't want to know where it came from periods of abelian varieties, but here's my complex number, and it should always give me e to the gamma k minus. Okay, so this is what's known. The conjecture is also known if k over q is abelian. This is Anderson, Greg Anderson. Who else is involved? So there are some cases in which we know this to be true, and there are some recent progress about average versions of this being true, average being when I average over a CM type, but in general, it's quite open. Okay, so therefore, this is up to now what I've been telling you is the interpretation of this number. This number gamma k, which came about as a constant term in the expansion of the logarithmic derivative of the Dedekind Zeta function, is thought to be logarithm of a bunch of periods coming from abelian derivatives. Okay. The next thing I want to tell you about this number, these numbers, is
it easy to tell us what P11 is in this case?
In this case,
yeah.
it is the real period of the elliptic curve. Yeah. You see, there is nothing to do because a CM type has only one element. I'm an imaginary quadratic field, right? So it's not a mystery how to go from sigma phi to sigma tau. Okay. So that's chapter 1. Now we begin chapter 2. It's 3 hours, right? Chapter 2 is, so that, basically what I'm going to do is in this talk, I'm trying to tell you why these numbers are considered to be very interesting. And if we have time to talk about results, we will. But even if you go away thinking these are interesting numbers to study, then my goal is achieved. Okay, so here's one reason why I think they're interesting, because they capture 2 rules. The second thing has to do actually with the problem that arises from coding theory. In coding theory, you know, I was telling this to some of our friends at lunchtime. Coding theory is a way of representing information. Coding, the whole theory of code is about how do I represent information, and then you have some constraints like it has to be error corrected. That is, when I'm transmitting that information, if I lose some bits, somehow what I get should allow me to be able to reconstruct what I sent in the first place. Right? This is right. Now, it's long been known that algebraic geometry gives you a supply of codes. Namely, if you take any curve over a finite field, the set of points can be used to construct a code. And usually these codes are pretty good in the sense they come close to something called the Gilbert-Warszawa bound, which is a theoretical obstruction for how good a code is. You see, the goodness of a code is measured by a couple of parameters. One is the number of code words, and the second thing is the distance between code words measured by some metric. It's the distance that allows you to do the error correcting. And certain curves are really good for this. Curves with a lot of points over a finite field tend to generate good code. So Ihara at one point was interested, therefore, in looking for curves over finite fields that have a large number of points. Large number meaning there's an obstruction given by the Way bound on how many points there can be on a curve over a finite field. Curves that push that bound, push the limits of that bound, they're considered good curves. So what he showed is that if I take over FQ, curve of genus G, and look at now for my K, instead of a number field, I look at the function field, FQ, not FQ of X, the function field of X. So it's some algebraic extension of FQ of T. Now one has, just like in the number field case, one has a zeta function. But the nice thing about the zeta function in the function field case is it's a rational function. And you can write down what it is. It looks like this. It's a product. I equals 1 to G, 1 minus pi J U, 1 minus pi J bar U, over 1 minus U, 1 minus QU, and U here is Q to the minus S. Okay, so there are certain complex numbers, all of absolute value Q to the half. These are so-called Way numbers. And the zeta function is a rational function. On the top, you have a polynomial of degree 2g, where g is the genus. And the bottom, you have 1 minus u and 1 minus qu. Now you can go ahead and look at the logarithmic derivative and define the gamma k. And when you do that, you get a formula. You get a formula which shows that, let's see. So you get a formula like this, gamma k over log q. Looks like this. Let me just write it down. So n sub m is the number of points. X of f to the m. Okay, so you get a formula like that. Now all you need to look at this qualitatively is the following: if n sub m is large, especially for small values of m, this will tend to be negative. Okay? If n sub m, and that actually works the other way around too. If gamma k being negative is essentially the same as n sub m large for small m. Small m means that over small extensions of the base field, I'm getting lots of points. Therefore, it becomes interesting to study the sign of gamma k. That was one of the things that Ihara did develop. Now let's look at this. Having understood this, let's interpret this in the number field case. What does it mean? Well, having a point of small degree in the number field case means having a prime of small norm. In other words, small primes that split in the field is the thing that determines the sign. So based on that, Ihara made a conjecture. So Ihara conjectured the following, that if I consider now the cyclotomic field, again back in the number field case, well, this field has no small primes that split, because for a prime to split completely in that field, P has to be congruent to 1 mod m. P splits completely K, if and only if P is 1 mod M. You all know what I mean by splitting completely? You see, the ideal generated by P in Z, if I look at that ideal in the ring of integers here, it won't stay a prime. Even though I started with a prime ideal here, when I look at the ideal it generates upstairs, it can factor. If it factors as much as possible, you say it splits completely. Okay? And primes that split completely are very useful for a number of reasons. Basic, like baby class field theory, tells you how you identify primes that split completely. So in the cyclotomic case, splitting completely means is the same thing as saying P is congruent to 1 mod M. Now, you see, if I give you an M and I ask you find me primes congruent to 1 mod M, what could they possibly be? Well, you could start with 1. Well, 1 is not a prime. Then the next one is M plus 1, possibly might be prime. Then 2M plus 1. Whatever it is, this prime has to be at least M. And so from one point of view, there are no small primes that split completely. And therefore, his conjecture was that gamma K, in this case, should be positive. Yes. Now, it turns out gamma minus 6, 4, 4, 7, 7, 9, 0, 1 is minus 0.18. That's the first one. And this number is. So there's a kind of mystery here. What's going on? So firstly, his conjecture is false. So because we have. But since we're out of time, what I will say is the mystery is this. We expect gamma M to be negative infinitely often. This is known to be true. This is a result of Ford, Luca, and Murty. It's known to be true if something called the Hardy-Littlewood conjecture is true. Hardy-Littlewood conjecture is about, for example, the conjecture that says there are infinitely many primes P such that 2P plus 1 is also prime. Well, Hardy-Littlewood conjecture generalizes that to any sequence, A1 P plus 1, A2 P plus 1, A, all of those being prime simultaneously. If that conjecture is true, as some people think is true, then this is true infinitely often. I should tell you that when Ihara was first told about this, he said Hardy-Littlewood is probably false. So people have different opinions on it. So now finally, I should really end up with a theorem, maybe. So I'll tell you the following theorem that, did I say that? Yes. So this is a result of my former student, Murtada, myself. What we show is that this gamma Q, that Q is prime, it becomes a very subtle problem now, getting handle on this gamma Q. What we showed is that it's bigger than minus 11 log Q for almost all Q. In other words, density 1. So these are now attempts to say, okay, it seems it can be at negative. How negative can it get? And it turns out that this is the first result that shows unconditionally that there are lots of conditional results, and conditional meaning conditions that go beyond what the Riemann hypothesis can prove in attempting to get your handle on these constants. But this is unconditional. It shows that most of the time gamma Q doesn't get any worse than this. And it looks like maybe if you work harder, you could squeeze the 11 a little bit, make it smaller, but probably you won't be able to show gamma Q is positive for almost all primes this way. Okay, clearly a lot more to say, but I hope you're intrigued enough that you go out and read all the papers about Euler primes.
Is there a version of Charles-Solver in the or a conjecture, Holman's conjecture?
Let's just think now. Firstly, what do we mean by theory? We need differential forms, which we don't have. Yeah, and then so the definitions are problematic first, but I don't think anybody's tried to formulate it. Maybe it'll be easier to try to do it p-adically, where you have p-adic Hodge theory, and so a lot of what I did there, and probably there one can formulate. I don't know if it's been done.
Yeah. So you much earlier you had said, as soon as you introduced gamma k, you said, well, this allows us to be averaging over k. When you were building things up, I was expecting that you would restrict to a particular classical structure or something and say, here are things that we can say on average about gamma k.
Right. Yeah. So I can tell you results like that. I'm glad you asked. I didn't plan it. So especially the ones that are most pliable for this kind of analysis are two families. One is quadratic fields and the other is cyclotomic fields. So what we showed is that Ihara asked us a long time ago how these things grow, and we proved with Ihara the following result, that So Ihara proved the following. Assume Riemann hypothesis. He showed that this gamma constant is trapped from above by a constant times log of the discriminant. So by the way, we're now entering into hardcore analytic number theory, so be prepared to hear logs a lot. Triple log. So log of the discriminant, but so it's less than or equal to C2, bigger than or equal to minus C1 times log of the discriminant. Okay. Assuming the Riemann hypothesis. And then this is Ihara. Now, what we showed is that in the case that K is a cyclotomic field, you see, in the case of a cyclotomic field, roughly speaking, the discriminant is like m to the m. Roughly. So log of the discriminant is like m log m. So log is like log m. Right? And on the other hand, this is like, its upper bound is like log m and the lower bound is like m log m. The big gap. So what we showed, what we showed is that if m is prime anyway, that the gamma constant for this thing is bounded by log m squared, assuming the Riemann hypothesis, and m to the epsilon unconditionally. Okay, so that much still no averaging. Right? But then on average, it behaves like the logarithm. But if I average this over m roughly m, divide by the number of m's. So this means between m and 2m, then this is bounded by log m. So then you start to get closer to what, this is unconditional. You get closer to what he said was the upper bound assuming Riemann hypothesis. And Fouvry, I did this for m prime. Fouvry showed that if I remove the prime condition and just look at all m's and remove the absolute value, so now you allow oscillations, then this is actually asymptotic to log. So that seems to be the right size. Log m seems to be the right size for this thing. So now we're worried about these constants. Okay, but that's an instance of averaging.
So your averaging does not assume the Riemann hypothesis?
No, this is unconditional. So is this unconditional.
I thought those were the same.
And you need Riemann for this?
For this thing?
Yeah.
Because you see.
No, you need it for which things?
So for a general K, you need it for all the orthogonal functions.
For the orthogonal.
Yeah. By the way, one more thing to intrigue you here, I should tell you. You see, you should be surprised. Why are we using the Riemann hypothesis? Because these are questions about s equals 1. Way away from s equals a half. See, Riemann was all about the action at the center of the critical state. We're way at the edge where you're supposed to know everything. You know, you proved the prime number theorem already, right? But the logarithmic derivative seems to know what's happening at the center. And the non-trivial zeros of the zeta function insinuate themselves in the estimate. You can't get away from it. Very strange thing is the way these things are interact. I find that more fascinating than the theorems themselves. The way things interact that you wouldn't have expected.
Let us thank our speaker.